week 3 and 4 was kind of just introducing you to the equation of motion. That's week 3. Then we talked about dynamic properties and definitions within those equations in or during week 4. So week 3 and 4, they kind of introducing you into the equation of motions and the definitions of the elements within the equations of motion. Then after that, from week 5 up to last week, week 7, we have considered excitations to be applied onto the single degree of freedom systems we are considering. The excitations we start with talking about, they were harmonic motions, and which are kind of similar to periodic excitations as well. We took about 2 weeks, week 5 and 6, we spent week 5 and 6 talking about harmonic motions. Then last week we talked about pulses, just one single pulse, something like this, and we talked about the shapes and the forms. So that's what we've done so far. We're still talking about single degree of freedom systems, but what we talked about so far, it's kind of synthetic motions inputted into the equation. Synthetic motions, they are simplified motions like the harmonic sine function, cosine function. And last week we talked about the single pulse motion, in which we talked about the 3 shapes: triangular, half a pulse, sine, and rectangle, right? Those motions can be equivalent to many real-world applications, like truck hitting a building or wind load hitting a building, or in relation to harmonic motions, we talked about the well use of such theories was about conducting tests on existing structures to determine particular properties. So that was just a quick summary about what we've been doing from week 3 up to week 7. Week 8 this week, we will be talking about non-harmonic and periodic excitation, and basically we're talking about something that we cannot model by an equation, like what was the case for sine or cosine or the pulses we've gone through last week. Non-harmonic motions, simply they can be something like what you see here, like a real ground excitation. And these very famous ground excitations took place in the past, and engineers are still using nowadays because they kind of involve very decent and clear frequencies and amplitudes that can be a very good case study to consider when people want to study and evaluate particular theories, right? So these motions, they are non-harmonic. But by the way, the horizontal axis here, it's the time, and the vertical axis can be acceleration or velocity or displacement. But with those real world ground excitations, basically the vertical axis is the acceleration, and the horizontal axis is the time it's taking. So what I'm trying to say so far with the harmonic or pulses, we have a defined synthetic ground excitations which we can model or simulate by an equation. So the second response is the right one. The key thing we have in this week, it's non-harmonic or periodic excitations. We mostly dealt with harmonic, if you remember, with our week 5 to 6 topic. So this week we're going to know how to deal with such excitations and what engineers do when they evaluate building undergoing such excitations. So that's it. Usually it's not possible, like with those type of real ground excitations, it's not possible to come up with an equation to define the force imposed on the equation of motion. Just a quick reminder, this was the equation of motion. I'm just jumping a few pages here. You all remember this is the equation of motion, which I've introduced you in week 3. And we need to define the equation with motion. So if it was harmonic, we can come up with a function like sine or cosine. If it's a pulse, we can come up with a function like what we've seen last week, and there are different methods to apply them. This week, it is, again, it's non-harmonic, it's a time history, and we cannot have a formula to define that. So today we're going to see how we're going to deal with such situations. And that's basically the key learning outcome from this week. All right, some problems cannot be tackled only by numerical time stepping method, and that's why I was mentioning to you in the previous week when I start talking to you about one of the integral pulse method. I did mention it to you last week, and I said to you this method will be basically the key approach to resolve real earthquake forces imposed onto structures, and talking specifically now more about the single degree of freedom systems, because that's what we're talking about now. So yes, the way to solve such problems is by numerical time stepping methods, and there are many available from math, but we will focus on two of them in today's lecture, and you're going to be practicing them and working out some examples. All right. Now, before I go to the methods we're going to be using, there is a kind of more integral-based method. Integral-based method, it is similar to what we did for a single pulse as an alternative method when the time stepping, if you remember, the time of the pulse is shorter than half of the natural period. Remember that condition last week? We said we can integrate under the curve. Now, there is a process that engineers use where they can actually focus on the, I'm just trying to zoom into one of those ground motions. So what they do, basically, they go to each pulse within the time history and try to integrate under the curve in order to find the energy developed by such motion and start converting that energy into whatever we need to calculate, whether displacement or velocity, right? And end up solving our equation of motions under real ground excitation. So that's one of the approach, is to use an integral method, which is called also Rank-Kutta method. Now, this method, as I said to you, it just requires a large number of by hand. Typically, it's complicated to do. Same as the numerical time stepping method we're going to be using. We're going to be using Excel to do that. But with this method, the Rank-Kutta or the Denel integral method, it's going to need solving differential equation, which we can't even solve by Excel programs. We have to use Visual Basic kind of integration processes to do so. Now, again, these methods, they deemed not to be useful and not stable for some type of excitation, especially if the time stepping was very, very large. Like sometimes we have, because, you know, there's a lot of random situations here. We got areas where the ground excitation is getting less frequency than other areas. If you focus here, you can see got ground excitations with particular frequencies, but when you get to this range, for example, you have more condensed frequencies. If you remember last week, we said your time step have to be less than particular value, so you cannot really confirm this is happening within such method. That's why Rank-Kutta method cannot be always useful in many applications unless you're studying very well-known defined excitation from which you can confirm the time stepping won't be unbalanced. Now, the first method that I was introducing to you in the following slide Here it won't be covered in this subject or this lecture. We won't be using it, but just for you to know about in case you can experience it in the future. There is something, yeah, there are time stepping which researchers use, but they can be used for very special excitations where they can confirm the conditions of the ground excitation, which I will clarify further to you. So basically, this method won't be something we're going to apply, but it is available. And again, more details are available in the textbook. And in summary, what they do with this method, they go through each pulse within the real excitation and find the area under the curve or integrate under the curve, then convert that energy they calculated into other properties we need to calculate. But as I mentioned, this needs to be under specific conditions, and it won't be something we're going to practice in this subject. So what we're going to practice are other methods, which I will get to. Now I'm coming back to the time step integration method, which we will be applying. Is about predicting these properties. As I said to you, the displacement, the velocity, and the acceleration, not of the ground, of the structure. So remember, someone will say, this is the ground excitation. That's how the ground was moving at. That's the ground. We need to determine what's happening with the single degree of freedom system, which we're supporting. So if this is our structure, simplified as a single degree of freedom system, then this motion is actually applied at ground level. And what we really want to find, it is the displacement, velocity, or acceleration resulted in the mass in the single degree of freedom system, in this mass, basically. That's the aim. There are several methods. As I said, the first one, we've got the Duhamel or Rank-Kutta method, but this is kind of this can be used. It is very accurate, that's right, but that accuracy will come only under specific conditions, when all your pulses within the time history are below particular value, when the time step or the time of each pulse is within acceptable time step value, which we cannot guarantee for all cases. You have to go through a different study, then evaluate its applicability. The other methods, they are purely depends on integration of the steps, which we will be doing together. And that's basically what these slides are mentioning to you. Now, these computations, as we're going to see, they start with particular initial conditions, which we're going to see. Sometimes you are evaluating a structure which is pre-displaced or under initial velocity or acceleration, so that can be considered. And as I was saying to you before, the methods that I will introduce you to, they can be bounded or not bounded. Bounded or not bounded means they can be within specific conditions, like the Duhamel Rank-Kutta method, or they can be with unconditioned. So it can be applied on any type of motion and can be applied with whatever time step you will be applying. And we're going to be seeing that in the examples we're going to go through. So the methods we're going to be having, they are listed on this slide. The first one, again, some of you may have already practiced these kind of activities in math maybe, or applied math. So the first one we have here, it is central difference method. Right? And we will be applying this, and you're going to be asked to apply and use it in your second assessment. It is simple to operate on spreadsheets, but less accurate. So this is kind of one of the basic methods we use. It's less accurate in terms of the response of that single degree of freedom system, but it is very simple to apply and can be calculated without a lot of computational steps. Newmark method, by its own, it's got three kind of branch method. And what we're going to be using is the first one here. The rest is kind of just gives you more accuracies and different conditions to work with. It just gives the engineers opportunity to use different methods, depends on the condition they have. The condition I'm talking about is comparing the available time step of integration with the actual time it takes one pulse within a time history to happen. So first, we have to make sure these kind of excitations are covered. And you know, over like previous decades, they used to come up with those methods because computers were not that very powerful. Nowadays, by few clicks, you are able to do all the methods I'm talking about and just comparing between each other. Nowadays, it's not a big deal really to have all those methods built by one of the many softwares available, or model them in Excel, so be it, and then just compare and see the accuracy, right? You always, because nowadays the access to computers are not as easy as before. So it's really whichever one you're going to be learning, you can apply the other ones. And you're going to be able to see, when you see the response and the results, you will be able to determine whether they are making sense or not. So basically what we're going to be applying, the central difference method. We're going to practice it, and we're going to practice this first type, the constant average acceleration method, which is one of the Newmark methods. Newmark as well, they got other advanced method, which is linear average. So basically, instead of taking constant value between 2 points, they're gonna have kind of a linear average. So if I show you kind of just a quick, here we go. That's really what we mean. So there are 2 points within your time history. Remember, this is 2 points within the time history I showed you at the start, the ground excitation. So that's, again, let's assume one of the ground excitations. We're trying here to talk about 2 points within that time history. That's what we're talking about here. So taking 2 points and trying to find a mathematical way to time step it. One of the methods by Newmark, it is just to take a constant value. So they go midway between these 2 points and adopt this as the value, the averaged value between the 2 points. Alternatively, the linear averaged is they, instead of taking a constant line like this, they're going to take just a linear line from one point to another. So this will just require more computation to do. And as I said, nowadays, it's really not really difficult thing for our personal computers to do that with. So what we're going to practice, again, we just want you to experience the real application of those methods. And what we're going to be using, as I said to you, we're going to be applying these 2 methods as indicated on this slide. You're going to be basically using the central difference method and the constant average method, and you will be asked to show such work in your second assessment related to these 2 methods. Wilson method, it's another modified one, which was presented by Newmark, and it just got some other features that can take into account more complicated situations in relation to the time history. Because sometimes if you've got some smoothing within the curve, it may not be correctly predicted, right? And as I said, if the most accurate method is actually this one, in case if their conditions or boundary conditions are met, right? Because here with this one, you're kind of calculating all the area by integrating the lines. So you're kind of using calculus. So whatever line we have, we're going to calculate all the area underneath it without averaging. You're not taking it point by point. You're actually looking at your curve and calculating all the area underneath it, which should give you the most accurate results. But again, this method will only be accurate if we have the right choice of time step, which again, I can tell you, if you correctly modeled it, nowadays it's not too difficult to do so. We have really powerful computers to make the time step as small as 0.01. Doesn't matter, right? But sometimes your computer will be slow, I can tell you, and maybe when you do these things, your computer may get may just freeze, yeah, cannot process further. If you want to try it, like even when we're gonna apply our central difference method or Newmark method, try to solve them with very, very small time step, because we are the ones to specify the time step. If you go to very, very small time step, then you may end up with unwanted results, or your software will take a lot of time to really solve it, or sometimes it may just get crashed or not able to solve. So you may have this experience as well. So in summary, this week we're going to be dealing with real ground excitation. We want to find how a single degree of freedom system or a structure above the ground will respond to such ground excitation. The well-known methods to use, we use time stepping methods, and there is integral methods. Integral methods, they like run quota, like what we simply did for a pulse. They require more processes to do, which we are not covering in this subject. We're going to be using the time stepping integration method, where we have discrete points, and there are several methods available. Some of them are listed here, and the ones that we're going to be applying and practicing are the central difference method and the constant average method, the constant average acceleration method, which is part of or one of Newmark methods, right? Now this slide will just give you an idea about what we mean with computational stability. That's what I mean is there are methods which we are required to make sure whatever time step we choose, time step is delta t, right? This is a number where we are as researchers or as engineers should use and then solve and integrate for the ground excitation, which, as I said, maybe 30 years ago, when computers were not that powerful, people were very careful in deciding on this number. They can't go as small as 0.01. Yeah, computers won't have this strong memory in their systems to keep calculating these numbers. They can't get it. It's expensive. The way we used to say that is an expensive process. That's why we need to find the most appropriate method to apply. Nowadays, whichever method should be fine. Yes, it may take time. It may take maybe, if we're talking about long time or duration, it may take 5 minutes to do so, but it's not a big deal. Yeah, we can still wait for 5 minutes for calculating the response for like an excitation like El Centro here, which goes for how many seconds? I think I'll give you, maybe this goes for 2 seconds or 5 seconds overall. We can still do it. So what are those conditions, or what do we mean with conditionally stable procedures? What does it mean? We have methods which are known to be or called conditional stable procedures. They are if we have to decide on a time step which is shorter than a specific limit. So if there was a method that will tell us you are able to use it when you choose a time step smaller than a particular limit, then this means those methods are conditionally stable methods, and we have some of them, as you're going to see later on. There is some other methods which are unconditionally stable procedures. That means it really doesn't matter whether they don't give you such limits. You can use whichever method you like to use. For example, the constant average method, which we will be using, and it's this one. It's this one here, the constant average method. It is basically unconditional stable. So really it doesn't matter. Whichever time step you use, it should give you results. But the accuracy, again, you need to work it out, which we will be discussing later on. So how you measure the accuracy is you keep reducing the time step until you start getting the same results. That's what we talked about with meshing last week. You remember when I start showing you how to mesh your RCB building model? Some of you may start with 1 meter mesh. Some of you will start with 0.75 mesh. You can try again, do it at 0.5, half a meter mesh. If you start seeing the results are not changing, the stresses or deformations of your building are not changing. But remember, as you go smaller with your mesh, you will have more elements. So it's going to take more time for you to do the calculations. So it's, yeah, as I said, but nowadays, it doesn't matter if you have extra 3 minutes to do the calculations, really. So how to, talking about the constant average method, this one, it is unconditional, but still you have to check the accuracy of what you're doing by changing the time step to smaller and smaller until you start getting constant results. That means these results are the correct final results. Now, there are methods like the linear acceleration method and the central difference method. They are conditionally stable procedures. What does that mean? It means that we have to check this condition. So we have to divide the time step over the natural period of the building we are studying or evaluating, and making sure this ratio is less than this figure, right? That's what the researcher who have developed this method, Newmark, he came up with this figure. He's finding if your ratio between the time step that you've selected and the natural period of your structure is less than, or should be less than 0.551 in order to get appropriate results. Otherwise, your results, for example, you can try when you start modeling. So this is the response, for example, plot. You may start having your response to be like this, just flying, which is because the integration start blowing up. They call it in the textbooks blowing up results. You're not able to, you're just going to keep adding, but it's not kind of because you have missed some of the information for the ground history. So you're not anymore giving the right response. Right? That's why typically we try different methods to work out the answers. So basically what we're saying, the central difference method and the constant average methods, the central difference method and the linear average method, which we're not applying here, they are conditionally stable methods, but the constant average methods, it is unconditional. It says, it's actually saying here. Yeah, it says that here. I don't need to. It says that here. So this one, the constant average method, unconditionally stable. And we're going to apply this. It's really doesn't matter whether we, it doesn't matter what time step we choose. But the central difference method, no, it is conditional. And as it's indicated here, but less accurate. All right. And these are, again, the methods we're going to be applying in the subject. All right, so for the central difference method, we need to make sure this ratio again is less than 1 over pi, okay, which is 3.14, etc. All right, so that's basically what this slide is referring to. You need to understand the methods we're going to be applying. You need to understand what we mean with conditionally stable or not stable. We will be practicing two methods. As I said, the central difference method, it's basically conditionally stable. We need to check the ratio. And the other method we're going to be applying, it's the constant average acceleration method. And as indicated below here, it is unconditional. So it doesn't matter what time step you're going to be using for it. And all these kind of things can be practiced as you do your second assessment. Central difference method, they're going to define 2 points, and these 2 points, they are any points within the curve. So point 1 and point 2 here on the screen. And the point we are at, or at which we need to calculate the velocity, is is the blue one. So what central difference method says to us, if you want to calculate the velocity at the blue point, which is here, you have to take the difference between the displacement of the next point minus the displacement at the previous point and divide it over the time between. The time between is this, which is 2 times delta t, because delta t is the time step between the points. That's basically the definition of central difference method from math. If we differentiate this relationship by, again, math, you will end up having this formula. So that's up until now, we are just talking math. To apply these kind of formulas, which are known to be the central difference method.
So U double naught means 2 times integration or derivation, or is it that sibling U times dot 1 dot in
yes,
above
that's right. So yeah, this is this U is the displacement.
Okay.
U dot is the
first derivation
velocity.
Okay.
And U double dot is the acceleration. Yes.
Okay.
Yeah. Now, so far, we all know what's the velocity and what's the acceleration. And we're coming now to the process of applying those formulas on our dynamic problem, which is this one here, which we talked about in week 3. So this was the equation of motion we all know, which is defining the mass by acceleration, damping by velocity, and stiffness, which is coming from K multiplied by displacement, right? So what we're doing here below, we are just substituting, and we substituted the acceleration we have formulated from math below, and we substituted for the velocity, which we also had here. And last thing here is our displacement, defining the stiffness force. So far here, from 1 to 2, we just substituted for the acceleration, velocity, and the displacement is defined. Now, next step is, again, we're going to go back to math. Next step is basically what we're going to be asking Excel to do for us, and that's what I'm going to ask you guys to practice. So next step here, it is a method. It's applying the method, right? So what does this kind of flow chart shows you? Shows you a summary, how to implement the procedures for using the central difference method to find the acceleration or displacement. So basically, what's required? This is required. We need to calculate the velocity of the system. We need to calculate the acceleration of the system. And also we need to calculate the displacement of the system, right? Remember, let me clarify this to you again. What's this? This is coming from the time history. PI, it is the time, it is whatever action, typically it's acceleration, coming from the earthquake. So PI, it is the ground motion. It's a motion like this. It's a motion like El Centro. One of the famous motions we use in studying how structure gonna perform, right? So P, it is the value. So PI means at the first time step, P2 at the second time step, P3 at the third time step, and that will be given to you typically, all right? So that was the PI. And sorry, I got a problem with zooming. So U, it is the displacement of the single degree of freedom system or the structure we are studying. Let me just put my single degree of freedom system here, which is standing on a stiffened column, right? So the PI is at this level. This is the PI, which is the ground excitation. The UI is the displacement of this mass, okay? And we're gonna need to find this answer. And sometimes we will also need to find the velocity, which is 1 dot. And sometimes we need to find the acceleration, which is 2 dots. Because you know the acceleration, if we multiply it by the mass, it will give us the force. Right? So it depends on what we want to use. And as I said to you before, at different topics, different weeks, we mostly work with displacement and with acceleration, because displacement give you the serviceability, behavior of the structure, and acceleration give you the force. And the force will give you many other things. Will give you the bending, will give you the stresses at the base of the core, etc., etc. Okay. The velocity is kind of useful if you want to design a damping system in your structure. Right, so that was really the definitions of each parameter. The parameters we have in the equation of motion, they are basically what's happening with the system, what's happening with the structure we are evaluating. This side of the equation is talking about the motion coming from the earthquake, which will be typically given to you in the questions. So this slide really, it helps you to build an Excel file, something like this. And I will let you do it now today. In the second hour, I will just leave you guys working on this. I will not give it to you. I want you to do this by your own. This is one of the examples we're going to be doing. So how I did this Excel file, I did it based on this flow chart. So what I want to calculate this curve, the blue curve. The blue curve, if I click here, it's basically the displacement from equation 2.2. Where is it? It is here. Now, to calculate the displacement at each step, you have to calculate this pi. Calculate this pi, you can see it's some function. I will clean this. Let me use this kind of highlighter better. So to calculate the this character or property, you have to find this value up here, right? So to find all those properties, the way the flowchart have set you up, just kind of helping you with all the parameters. A is defined here, B is defined here, and etc., etc. So all what you need to do in order to build such sheet is actually summarized to you in this page. And this is basically what we're doing. We're applying a time stepping method based on the central difference method. We are integrating between the points in a time stepping method, not by finding the energy. And yeah, so as I said before, this is the central difference method. It is conditional. It is a conditional method, and we are required to check that the time step is below particular value. How to make that check is we divide the time step we selected. We just need to make sure the selected time step over the natural period of the structure we have is less than 1 over pi. And so typically, if we have that ratio less than 0.1, then the response will be adequately calculated. All right, because typically the time step can be set between these two figures. Right, so I think what we're going to have now, and I will let you guys work on it. We have this example, right? So today's lecture, the second half of today's lecture is for you guys to work on and share with me what you're doing. Okay, and what I want you to do is to do this example by doing something like this. So I know it's going to work. And why I want you to do it now, because this is going to be the main step to work on your second assessments. You're going to be doing many curves like those, or this solution actually is going to be part of what I want you to do in your second assessment, which I will also talk about next week. Okay, so today you just need to calculate the response of a structure, whether displacement, or whether acceleration, or whether, let's see what the question want you to do, and then we go through it. So they're saying to us there is a single degree of freedom system. It's got this mass, it's got this stiffness, it's got this natural period, right? And the damping is also given to you. They want you determine the response of this system. So they want you to find the displacement of the system, of that single degree of freedom system, to this defined motion. Okay, so the motion here is very simple to start with. And next week, and in your assessment, you're going to be given ground excitation. It's more complicated. So I just want you to be confident about solving some simple examples, and then we go to the next system. All right, so they're asking you to apply below by using the central difference method. Okay, and make sure when you do this sheet, make it as accurate as possible, even better than what you're seeing maybe, but it does work. And I just did it here to check your work later on. Right? What I want you to take your time and understand those steps and ask me as much as you like. So if you want now, do you have any questions what I want you to do? I just want you to solve for this example, work on applying the central difference method, and develop a calculation sheet like what you're seeing here by applying that summary I showed you. If you have managed to achieve that, that will help you to really get to working on your second assessment. And same thing, you're going to be able to work on the other method that I'm asking you to do, which is the Newmark method. It's really not different, it's just same. So do you have any question now what I want you to do?
Can you keep in this slide so it's easier to do the calculations? Is it okay?
Which one? This one?
Yeah. So
yes, definitely. I will keep it, and you have all access. You all have access to those lecture notes, by the way.
No, sorry. So I can use this screen as equation screen and another screen as the slide and the Excel, so it will be easy.
Definitely. No, that's no problem. Yeah, I can do that. Yeah. So yeah, you can have a break or you can work on this, and I will be around and waiting for you all to tell me that you have achieved something like this, and I'm happy to compare my results with your results. Okay. So yeah.
Yes.
Yeah. Okay. So I leave you with it. Take your time and work on your sheets, and we'll take it from there.